The future is the nowhere, is the no-when. There is nothing there, not even space-time. And actually, as the universe is expanding, just I'm following the Big Bang, it is also expanding in time. It turns out, however, that for very brief time, the universe allows negative mass to exist. And that may explain the very mystery of the quantum.
Professor Avshalom Elitzur, a pioneer in the field of quantum theory, received his PhD without even a high school diploma, akin to Stephen Wolfram. He's a household name among physicists. Elitzur and his collaborator, Weidmann, discovered the famous bomb testing experiment, which many quantum physicists consider more profound than even the double-slit experiment. In today's episode, Elitzur proposes a new vision of reality for the first time. Starting from the elementary observation that time seems to flow, Elitzur articulates a unification of quantum mechanics and gravity by suggesting that space-time itself emerges from quantum interactions in pure nothingness. The longer you watch this video, the more ambitious it gets.
I think that there is something missing in physics, something that does not exist in the present particle models, in the standard model.
In some ways, this is the opposite of the retold dictum that space-time is doomed. According to Elitzur, it's more like it's not the death of space-time, it's the creation of it. Last week, we spoke to Julian Barbour about time being an illusion, and today we continue this excursion into the temporal with the opposite view. Time and the now are real. A consequence of this is that negative mass particles exist, challenging the foundations of modern physics.
Just by the fact that it could have occurred, it leaves a physical trace.
Though his ideas sound outlandish, the professor's track record for correct predictions, including experiments now being verified in the lab, suggests that we should listen closely to what he has to say about the nature of existence itself. Welcome to the podcast, Professor. It's been great connecting with you over the past few weeks. You have some new ideas that you've been working on about quantum mechanics, about time, perhaps even gravity, ones that you haven't voiced anywhere else yet publicly. So please tell me about them and tell the audience about them.
Shalom. First of all, thank you, Kurt. I should be thankful to you for this reason. I give many Zoom talks, but this for the first time, you gave me an idea when you invited me to talk on your podcast. I listened to some of the other talks and I said, wait, I also have a theory, a very ambitious one, a theory of unification. Yes, I think that I have a way to unify quantum mechanics with relativity, general relativity, and offer a step towards a real unification, a unified theory. Do I have a theory? Have I had one? I would be dancing on my way to Stockholm, but so it's not yet. But I believe that the model is getting more and more flesh and bones. And just preparing for this talk made me say sometimes, hey, that's not a bad idea. And it's about time to write a paper and present it somewhere. So I thank you for this opportunity for showing this in a raw form without mathematics, as non-technically as possible to you and to the audience.
So, Professor, how about we start with you giving a broad overview as to your journey in physics. What did you used to believe? How did you get into the field? What did you transition to, and what have you transitioned from, etc.?
My path in physics is, as you know, somewhat unusual. I did my PhD with Yakir Aharonov, who is still my mentor. He has recently celebrated his 92nd birthday, still very active, very sharp, and we are thankful for that. I brought him some of my own students as his grandchildren, and he is going to have grandchildren. Mm-hmm. I boast some very talented students of my own. It's unusual because I never finished high school. I never did a bachelor. I didn't do my master's. I just did my PhD. It took me just from out of the academia and said, okay, even if you didn't finish high school, why you have interesting ideas about physics, and why don't you do your PhD with me? And I hope that I have rewarded him with publications that I had and the discovery that I had since then. And many people know me through the Elitzur-Weidman experiment, which is, I believe it's the only experiment in the whole history of physics, which makes you smile. You're not, physics is not supposed to be funny, but the bomb testing experiment, you think about it, a bomb that could explode, but did not explode. And because it could explode, although it did not explode, leaves some physical mark, some real consequence, which is really paradoxical. And I had some other papers, some more technical. I had the privilege, together with my student, to be involved even in applications and patents and so on. And I've always been interested in the foundations of physics, the very foundations. This is a field of physics that today is not studied in many places in the world. Most of the money goes to what? Quantum computation, quantum communication, solid state physics, and so on. But foundations of physics is just asking the very basic questions about the reality in which we live. What is space? What is time? What is matter? What is energy? What are the relations between them? And we are very happy with some very strong and powerful theories that we have: quantum mechanics, relativity theory, quantum field theory, some advances in cosmology, and so on and so on. But still, we understand that there is something missing, and there is some discrepancies between these various descriptions of the world, especially relativity and quantum mechanics. There is a problem of unification. There are a few forces of nature. We have seen beautiful advances when more than a century ago, almost 2 centuries ago, Michael Faraday managed to show that magnetism and electricity are one and the same. That was an amazing and beautiful unification. And we always have the feeling that ever since Einstein has shown that gravity is not really a force, but a kind of space-time curvature, he himself was sure that within a few months, maximum few years, he will be able now to go back to Faraday's equations and Maxwell's equations and show that electromagnetic attraction and repulsion can be explained in terms of space-time kind of curvature, just as he did with gravity. And he failed miserably, and everybody since then who tries that keeps failing miserably. There's been a nice unification of the weak force with the electric force, but we still have the strong force, and still gravity and people don't know how to unify it even with the electromagnetic force. Yeah, I should mention all string theories, but I believe I have enough enemies anyways, so rather keep to myself some remarks which are not very. Actually, I've seen the talk with Susskind, your talk with Susskind,
Right.
to whom I have great respect, and I murmured to myself, for God's sake, all these efforts, and this is what you got after 50 years of promising that you're going to have the theory of everything. No way. Look. John Archibald Wheeler, he was one of the pioneers of quantum mechanics. He had ridiculous, he supported ridiculous interpretations of quantum mechanics, kind of Copenhagen or many worlds, which I don't endorse. But he once said something very profound, something like that. One day, we can be sure, there will be a theory which will explain all these phenomena in a kind of unified way. And when we have this theory, we will say to ourselves, how simple, how beautiful, how could we be blind for so long? None of the proposals today for a unified theory come even close to this vision, okay? With all the plethora of dimensions, spatial dimensions and compactification and so on. I may be wrong, but you have the feeling that the universe, the basic laws of the universe underlying all these things must be
Right.
very simple. Let me give you only one example. So here is an example. Remember the Bekenstein-Hawking information loss paradox. You throw things into a black hole, and then you lose information, and they are gone there forever. And then it turns out that if the black hole evaporates, what comes out of the evaporation retains nothing of the information of the objects that fell into it. It has been a paradox for many years. I believe, the majority of the community still regard it as a paradox. But here's my point. The paradox itself is so simple. Relativity theory forbids anything to come out of the event horizon. It's just relativity. You can understand it. You can understand how things fall there, and then you can see that the evaporation, if it comes out of the vacuum fluctuations, which are far from the singularity, then indeed information is lost. You can explain it to high school students very easily. Am I exaggerating in expecting that the solution to the paradox, which is so simple, devastating, and beautiful, would be also very simple, devastating, and beautiful? I mean, this is how usually things work. I may be wrong, but I'm looking for simplicity, and my suggestion for looking for a unified theory of physics is along the lines of simplicity and beauty.
Right. So let's hear this simple and beautiful theory of yours.
So I'm going to propose where do we want to look for the unification, in what realm of nature? And my answer would be paradoxical: nowhere at no time. And let me explain why. And my point of departure is a problem that many physicists dismiss. They think that it's not a physical problem. It's not interesting. They relegate it to philosophy. And I think that this is one of the basic questions of physics. And I want to say something about time.
Uh-huh.
So let's say something about time. You and I are talking, and we have talked a few days earlier, and time is going on. Here is the most prominent characteristic of time. Time is moving. Time has a passage. In space, I can remain at one place. I can go to the right. I can go to the left. I can go back. I can go forth. I can choose to remain in my place. Nothing like that is in time. Always we are in the next moment, and time seems to be flowing somehow. So this is the naive picture of time. Events come and go. We used to have Alexander the Great, and he killed many people and died. And then we had Genghis Khan, and he killed many people and died. And then we had Napoleon, who killed many people and died. And who knows who is going to be the next moron to make another war in the world. But events appear and go. Now we are in the present. We don't know what's going to happen tomorrow, but tomorrow will become the now, and then it will become past, and so on. That's the naive view. And the majority of physicists, nearly all of them, especially if they are doing relativity, special and general relativity, will tell you that this is absolute nonsense. Time cannot move. Time cannot pass, even at the level of logic. In order for something to move, move means being in one place at one time and another place at another time. So how can time, which is the parameter of all motions, move itself? It won't help you if you say that we move in time, because then you are specializing time. You make time the dimension on which you move, but then you may need the higher time parameter, and so on and so on. So actually, what physics tells you is the following: think about time as space. If I'm now in Israel, it would be silly of me to claim that Japan does not exist, or Tierra del Fuego, or whatever, or Andromeda, or other places in the universe. They are not accessible to me, but they all have the same degree of reality. All the universe, all the places in the universe, very far, very near, have the same degree of reality. And I have access only to this surrounding. The same goes with time. All these events, past, present, and future, in the four-dimensional universe, all of them exist together at the same degree of reality. So how should you and I think about ourselves, for example? So it's not one Avshalom and one Kurt who are talking with one another, asking questions and answering. We should think about ourselves as four-dimensional word lines from birth to death, and the word lines just curve according to our travels and motions and so on. And actually, each of us is a zillion of persons, zillions of Kurts, zillions of Avshaloms, each of them uttering a single syllable or experiencing a single syllable. Now, as silly as it is, this is not philosophy. This is actually the very idea of special and then later general relativity. Let me show how. Think about, this is the paradox that physics teachers love to show at class, the barn and the pole. Here I'm using a spacecraft and a tunnel. So I have a spacecraft and a tunnel at the same length, which I use, I don't know, for washing spacecrafts, and then a spacecraft at the velocity near to the velocity of light goes through this tunnel. So it undergoes Lorentz Fitzgerald contraction such that I can close the two doors of the tunnel for a brief moment while the whole spacecraft is within, because the spacecraft is contracted and it is much shorter due to its motion, due to its relativistic motion. Okay, but now this is relativity, and when I look at this from the viewpoint of the spacecraft, what I see is the spacecraft is at rest, and it is the tunnel which is at motion. So it is the tunnel which undergoes contraction. This way, there is no way in which the two doors of the tunnel, the front and the rear, could close because they'll break. The spacecraft is longer than the tunnel. Now, here, look, there seems to be a problem because in relativity, we have here inertial motions, and they are all equivalent, but they contradict one another. And they obviously the two ways look incompatible. They are not incompatible if you understand that the idea of simultaneity becomes relative in relativity theory. I mean, all of relativity is based actually on the relativity of simultaneity. So obviously, we do have the event in which the rear of the spacecraft is still outside of the tunnel, and the front of the spacecraft is already outside of the tunnel. However, there are two viewpoints, and according to one viewpoint, the tunnel is shorter than the spacecraft, and according to the other viewpoint, the spacecraft is shorter than the tunnel. Both of them are correct. So one of them is going to say, the one driving the spacecraft, hey, to the tunnel operator, you lied to me. You didn't close the two doors at the same time. You first opened, you first closed the one in the front and then opened it, and then the one the rear and opened it. So they were not simultaneous. What I'm saying here is that the Lorentz contraction, the very basis of relativity theory, is based on the notion of the relativity of simultaneity, which means that when you are talking about distant events, all of them coexist, past, present, and future, such that you can pick your frame of reference in order to see these objects as becoming contracted and the others remaining the same, or vice versa. So do we understand that for relativity theory, the passage of time is something that should be abolished from physics, just like an illusion? There is a very, very famous, and I'm going now to biography, to the history of physics. There is a beautiful book by Jimena Canales about the early history of Einstein and his encounter with the French philosopher Henri Bergson. Einstein was hesitant for a few years to say that actually the contraction, the slowing of clocks and so on apply also to our bodies, to organisms and so on, until he understood that he has to do that in order for relativity theory to be consistent. And then he had a friend, Michele Besso. It's a famous and very moving personal story. Bessel was a kind of a soulmate who worked with Einstein at the patent office when Einstein was just conceiving the theory of special relativity. And then he helped him some 10 years later with the general theory of relativity, and he was involved in his personal life, family, and so on. And then Bessel was a very good physicist. Einstein thanks him in the acknowledgement of several of his papers. He became a philosopher, much to Einstein's annoyance. And then he told Einstein, look, theory of relativity is, of course, beautiful, special in general, but something is missing, the passage of time. And Einstein told him there is no passage of time. It's only an illusion. And they were writing letters to one another. And Einstein told him, you have to understand that this is only an illusion. And then a few years passed. Sorry, I should say that it looked like a few years had passed because Einstein didn't believe.
Right.
And something happened that actually makes you really understand that, well, you know, time is passing. He got a letter from Michele's son, my father is no more. Einstein had 4 weeks to live. He died shortly after that. And the condolence letter, which he wrote to Bessel's son, is very famous. Michele has preceded me a little in leaving this strange world. This is not important. For us, dedicated physicists, the distinction between past, present, and future is an illusion, however persistent. Don't cry, son. Your father is not dead. He is alive. It just, in the past. So the young Bessel, the boy Bessel, the baby Bessel, all of them are still there. They're just not accessible to this part of, say, Einstein's worldview is longer, 4 weeks, 1 month than that of Bessel. But, the interactions between them keep going on.
Right.
I think it's ridiculous with all respect. But okay, there is no way to disprove it. And you can see that relativity theory rests on it.
Just a moment. What is ridiculous?
Quote, you don't know what you're going to do tomorrow, right? With your wash disher or whatever. Now, this guy tells you that it's already there. Whatever you decide, I'm sharing with our viewers that you got a new dishwasher. So what are you going to do with your dishwasher tomorrow? Are you going to be happy with it or not? Are you going to smash it because it will annoy you? Or I don't know what. You have not decided yet. Now, this guy, Einstein, tells you that the future Kurt is already there. I wouldn't say already, but he has the same degree of reality as the present Kurt and the past Kurt. Are you okay with that? Doesn't that strike you as silly?
Just for some context, the dishwasher here broke. We're renting this place, so the landlord had to replace it. And in case you're familiar with the backdrop, you'll notice there's a hole where the dishwasher should be. But anyhow, what you're objecting to is that the choice is removed, free will is removed, our experience is removed, or what?
Just whatever you think, you can't change your past, right? You can't affect your past. It's done. But you believe that you can change your future. And this guy tells you that you can't. You can pretend, you can believe in that, but actually the future is just as real as San Francisco. You're not in San Francisco now, or Calcutta, or wherever. They are real. They are not accessible to you, but they are just as real as the place where you are in now. So all times are just as real. So think about that all our lives, past, present, future, the whole history of the universe is there, just like single frames in a movie. And just for some reason, has to do with the second law of thermodynamics, we can talk about that. We have zillions of selves, zillions of Kurts, Avshaloms, and each of them resides in their own moment. Each of them has the memories of the previous ones. So each of them, he believes that he is the one. Okay, I believe that I am the Avshalom that woke up this morning, but he's still there waking up, and so on. What I'm saying is what is actually derived rigorously from special relativity. I've shown it with the Lorentz contraction. You won't have Lorentz contraction if you believe that there is some absolute simultaneity. Simultaneity is relative, which means that you need to have many times if you have events past, present, future, in order to pick the pair of events which make things shorter or shorter or not. Okay?
Right.
Now, Einstein himself was not very happy with that. He told Carnap that the fact that the motion of the now has no place in physics, he considered it as a matter of painful but inevitable resignation. That means that he was not happy with it. And many physicists say, okay, he was not happy. I'm happy with it. I still think that there is something very mysterious. And few people have this opinion. I believe Roger Penrose has entertained a similar idea. Paul Davies, many years ago, wrote a book in which he entertained this idea. Also, then later he said, no, I can live with that. But there is something very strange believing that, all our life, past and future are just there to the same degree. Am I the only one who feels this is uncomfortable? Are you okay with that, Kurt? We can make this dialogue more personal. Do you see that there is a problem here?
I see there's a problem with our experience of the flow and that we have a special moment called the now. So not only do we have a flow of time, which this contradicts, but there's a now that's distinguished. And that is to set aside all the issues with free will or choice.
There is something unique about this moment. It's already gone. Next moment and next moment. There is something fleeting, but always there is a moment which for us is special, is unique. And we believe that there is something to it. And physics tells us, no, all of them have the same degree of reality. And your belief that you are not the same Kurt as the Kurt who just brought the dishwasher or was frustrated for not having a dishwasher. and the future ones have the same degree of reality. You can see that Einstein was not happy with that.
Professor, the reason why you're sensing reticence is that while I may be uncomfortable with an idea, I am comfortable with the uncomfortableness. So it's difficult for me to evaluate which one is the one that I'm feeling. Is the one that's the visceral emotion, the one that I should prioritize, or is it the one that's the deliberation afterward? And is it even a deliberation? And regardless, to me, it's irrelevant because I have to put aside my own psychological disposition when evaluating an idea, as I have to look at a concept or a theorem or a result, whatever it may be, devoid of my own predilections. As the idea or whatever it may be may have merit, but I would have prematurely discarded it had I assessed it with an emotional lens. So in other words, while emotions are extremely important, it's difficult for me to evaluate which is the one that I'm feeling. Is it the uncomfortableness, or is it the comfort that I feel with the uncomfortableness, or is it something else atop that? Which of these nested hierarchies of I is the me? And lastly, I see it as something that is besides the point and could get in the way of the point anyhow.
Fair enough. So we can say, okay, you know what? This is a philosophical problem. We have all kinds of illusions, optical illusions, auditory illusions. So the feeling that time is moving could be just another illusion. However, that's not the only problem with time. There are other problems which are completely not philosophical, and they are a problem for physics. Think, for example, about the time asymmetry. Physics, the basic laws of physics are symmetric in respect to all dimensions of space. You reflect something in the mirror, then the physics that you see in the mirror under this reversal of right and left is just the same. Put a mirror here on the ceiling, and if I drop something, it will fall upwards, because physics does not distinguish between right and left, up and down, and so on. These are only local conditions. This is what makes the laws of physics so beautiful, that there is no distinction, that the laws of physics are symmetric. The CPT theorem, okay.
Right.
The same holds for time. For the basic interactions, there is also a complete symmetry. You take a basic interaction, ignore friction for a while, and then so you can reflect it not by a mirror, but videotape it and run it backwards, and the laws of physics are just the same. Okay, so there are beautiful combinations of these symmetries. Time and space, you reflect something in the mirror and then run it backwards, and you get all the things back. There are very nice exercises to show that with with respect to these symmetries, time is actually a dimension like the three ones. But the difference that everywhere where you look in the universe, so there is no left and right, up and down, back and forth. The universe is completely indifferent to that. But with time, every place I look in the universe, cups of coffee cool down. And every place in the universe where milk is spilled, there is no use crying over that spilled milk because it is irreversible. The whole universe points out, when you're talking about macroscopic events, always to the same direction. Entropy goes up. So that's a time asymmetry. How does this asymmetry emerge from the basic symmetries of the laws of physics? Good question. Many books, many answers. But it's not the only asymmetry, time asymmetry. The universe is expanding. The universe is not contracting. Although you could think that it could contract. So why is it only expanding if you don't believe that it will end up in a big crunch? Here's another asymmetry for you. We have mentioned gravity. So when you have black holes, you don't have white holes, even if they evaporate. So you have another asymmetry. And then you have this asymmetry, subatomic asymmetry connected with the weak force, which shows that actually there is a slight error of time even at the in the particles realm.
There's slight error of time, or there's slight left-right asymmetry?
No, but you also have a T-symmetry. Remember, this is what 't Hooft got the Nobel Prize for. There are a few interactions in particle physics which somehow distinguish between past and future. Why is that? How are all these asymmetries related to one another? Is there one master asymmetry from which you can derive them? Hawking tried to derive the second law of thermodynamics, the thermodynamic asymmetry, from the cosmological asymmetry. The universe is expanding, so there is more space for mass to occur. So this is the reason why disorder is growing. And then Daniel Laflamme showed him that it won't work. Suppose that the universe begins to contract. Would you expect at the moment that the universe begins to contract back that all cups of coffee would just, absorb back their heat and we shall become younger and so on and so on? You can show that this there is no mechanism that shows that. So it looks like thermodynamic asymmetry is not directly related to the cosmological asymmetry. Can you derive them from another asymmetry? These are all big questions.
Mm-hmm.
Do I know the answer? No, I don't. But that should be a hint that if we are unhappy with dismissing the passage of time as an illusion, we have good reasons for that. There are a few other problems with time that we don't understand. And you can feel that they are very strongly related.
Was the disagreement between Einstein and Minkowski about time as well? Do you want to go into that story?
Is there some Einstein wavered, but that's more a personal story. Einstein was offended by Minkowski's comment about him being a lazy dog for not attending his classes. But then when Minkowski heard that his former student had developed the theory of relativity, he said, okay, I can rephrase it mathematically. And I remember that Einstein mocked the idea first. He said, I heard that the mathematician has made my special relativity incomprehensible. Then when he had to develop the general theory of relativity, he had to pick up the Minkowski's view and appreciate it and make it part and parcel of relativity theory. It's tragic. I don't think that they ever. I wonder whether they ever spoke to one another. Whether there is no any record of them exchanging letters between them or whatever, or meeting. Was Minkowski happy, proud of his former student, although he called him a lazy dog? That's an interesting question. To the best of my knowledge, we don't know of any interaction between the two. But Einstein was arrogant about this geometrization of relativity, later completely adopted it. He wouldn't be able to do general relativity without the idea of four-dimensional space-time continuum, right? Because it is space-time which curves around mass. So there was no controversy. There was some, shall I say, slight dishonesty at the beginning or something. Or it was hard for Einstein to accept an idea which was not his own. We owe it to Minkowski, and it's just as genius.
Do you think that we're approaching a paradigm shift in quantum mechanics, similar to how there was the quantum mechanical shift from classical mechanics?
Absolutely. Sure. This is what I'm going to show. I believe I was privileged to be with a man of great genius, Yakir Aharonov, who is my mentor. And some of the advances that he has made during the last few years, last decades, are indeed a real paradigm shift. So some of these I want to show here. Okay, so my idea for unification begins with the assumption of becoming. I want to propose that becoming is real. You want to unify physics, different theories, with all due respect to string theories and other 10 dimensions and so on and so on. Just look at the 4 dimensions that you have. Look that there is something unique about time. By the way, we were talking about Minkowski. So in Minkowski's geometry, time is unique, is distinct. You have to add this imaginary ingredient to the t, right? Such that you have to make the t minus when you square it and so on. So Minkowski himself had to make time unique in this respect. You're just now giving me an idea. Perhaps that was what made the geometrization of time a bit difficult for Einstein to absorb. Because even in this picture, with which I'm trying to take exception, with all due respect, time is actually unique. You have to assign it the minus sign. So there is something unique already there. So I'm proposing to take this as the beginning of physics. Rather than adding other dimensions, let's look at time and say that time has indeed this passage, that the passage of time is real for reasons that we don't understand. So time, events are created anew. Okay, this moment, it is not that it's there all the time and just it is now the present Kurt and the previous Kurt and previous Avshalom are still in the previous. Just when I say it, it's so dumb. Never mind what I say. But
is it the same distaste you have for many worlds that you have for this block ice-like universe of time, which are just etchings in a block of ice?
You know what? Yes. Can you imagine that according to... So I should say that, Lev Weidman, with whom we have discovered the Elitzur-Weidman experiment, is a fan of the many worlds. I mean, he's now dedicating all his time to prove the many worlds interpretation of quantum mechanics. And I love him dearly. But I think it's ridiculous. Can you think about that? That from the moment we began this talk, there are zillions and zillions and zillions, I can't count them, of Kurtz and Avshaloms in parallel universes, just because someplace, whether it was my neighbor or somebody in a very remote galaxy, there was a quantum event. Well, now you have 2 universes, just because of that.
It sounds like you view the adoption of many worlds as a theory from a friend of yours as the same lamenting that you have when a friend gets addicted to hard drugs, where you're like, oh, what a shame, what a pity.
Look, I will deny if you say that I said that, but I'm going to say it, okay? When you are a physicist, when you're young, you will say, yeah, I'll be the new Einstein. I'll unify all theories and I'll have a unified theory and so on. Then you have to do your PhD and you have to look for a postdoc and you have this trouble and this paper is rejected and the other paper is rejected and people just, say, shut you up and you'll become more modest and you say, okay, I won't make the huge revolution. I make the smaller revolution and smaller revolution. This is how we become modest during our career. However, the ambition is still there. At least in my case, maybe one day I'm not that old. I'll manage to have the unification.
Great.
Every time that I hear that a good physicist adheres to the many worlds interpretation, I say, good, one less. I mean, the competition is very strong. He is not going to make it because they become so satisfied. It solves all the problems. And Popper's distinction between science and pseudoscience. Theory is scientific if you can disprove it, if you can refute it. No test that you can do that can disprove the many worlds, just as you cannot disprove the Bohm's guide wave or Copenhagen or whatever, they're equivalent. But people are very happy, people who endorse these theories, and sometimes they stop doing physics. They say physics is complete. We have solved all these problems. So yeah, I don't think so. I think that there is something missing in physics. And the missing thing in physics is the thing that every person in the street, children here in my neighbor's yard or whatever, they'll tell you time is moving. There is a passage of time. Now, you know what? Let's stop for a moment, because the moment I'm going to say that, people are going to, the penalty would be some logical paradoxes. If time moves, if the now really moves, there is a real motion of the now. What's its speed? So I need a dt, some kind of, I need a higher time. And some people try to invoke a higher time, but then that higher time would again require another higher time. Otherwise, you will have a block universe of 5 dimensions or whatever. So that would lead to an infinite regress. I don't know the answer to that. I believe I can show how to avoid it. But I understand why people don't want to do that. And I say, you want a breakthrough in physics, you want a paradigm shift, as you say in physics, you want to go forward. Let's take this as a hypothesis that indeed time is moving. Okay? So there's been a new event. It's not that it's there for all time and it is just this self which remembers, according to the model, that now there is a new Avshalom, but it's not new. I've been here all the time, but I have the memories of the previous Avshalom. So I believe that it is just this moment. Let's assume that every time that something happens, this thing is created. Okay? So we assume that events are not word lines. Perhaps there are word lines, but there is something drawing them. Okay? Imagine word line of me or you, but it's not frozen. That's part of the now, which is so unique. It may have, you hinted to that, to the problem of consciousness, which is so unique and it's still outside of physics. But how about saying that indeed the word lines are being drawn somehow, and actually every event is new? So when we feel that this is the now and this is new, perhaps we are right. And perhaps from this, we have to begin all of physics.
So are you saying, like, let's think of a stick of dynamite. You know, dynamite has this string in the cartoons. There's a huge string, and then you light the edge, and then there's a little fire, and it moves about it.
Good.
Are you saying that in addition to that spark, which characterizes the now, the string itself is moving?
Good question. Can you affect the past? Actually, quantum mechanics, and this is what I'm going to show, leaves some place for retroaction. Very limited. Things in the past are not completely fixed. So, this is what I'm going to show. We have some very good proof for that, some experimental works showing that. Actually, one of the interpretations of quantum mechanics is the transactional interpretation of quantum mechanics. John Cramer is the only living interpretation maker still with us. I had the privilege of meeting with him. He quoted our works many times. So it's a very beautiful interpretation. He takes the Wheeler-Feynman absorber theory from classical electromagnetism and applies it to quantum mechanics. And he says that every quantum interaction is the result of 2 wave functions, one going from the past to the future, one coming from the future back to the past. There was an idea that Wheeler and Feynman back in the 40s of the previous century have presented, which is mathematically very beautiful. And then Cramer applied it to quantum mechanics. Are you aware of this interpretation, the transactional interpretation of quantum mechanics?
Yeah, I actually have a Substack where I outline the top 10 most popular views of quantum mechanics, and then I explain them. I'll show a link on screen, not for you because it'll take us away, but the transactional interpretation is there as well.
Then I'm going to describe the two-state vector formalism by Yakir Aharonov, who shares with Cramer the same idea that every quantum interaction is the result of 2 wave functions, 2-state vectors, and that you have to bring them together. This is what I'm going to show. And I think that this brings new horizons to quantum mechanics to the point that we may really have a breakthrough and a new physics, which is, just as you said, is so new relatively to quantum mechanics as quantum mechanics is new relative with respect to classical physics. Yeah. But then again, if the retroactive models, interpretations of quantum mechanics are correct, that's another indication that there is something still ill understood about time. The fact that you can, in some cases, affect the past. So even the past is not fixed.
Now, before we get into the details with the slides, when you talk about retrocausation, people hear that and they think time travel. So what is your distinction between those?
No, if you really believe that there is a becoming, so we have block universe, which is the dominant view, the orthodox view, and what I'm proposing, the alternative is becoming, that actually says that there is events are becoming, then time travel is not possible because the past is really dead. Perhaps there are world lines. Actually, Lee Smolin once said that block universe is correct about the past. So you suggested that, there is something which creates the world lines. So perhaps the past is somehow there, but the real world is just the present and it is being created anew. I don't know. But then that means that you can't travel backwards in time and kill your grandfather and so on. Once again, there are people who do believe that you can go backwards in time, but then in order to prevent all kinds of grandfather paradoxes, they invoke the many worlds interpretation. So they support one ridiculous idea by another. I don't find it really exciting. What I'm proposing is something different.
Now, speaking of ridiculous conjectural ideas, a deliberation that I was toying with is, how do you maintain a notion of having a fixed future given a past while leaving room for choice? Can you do so? Can you make those reconciled or harmonized? So one way is that rather than selecting from different possible futures, which is what we traditionally think of as what free will may be, or choice in general, what if you have a selection of different pasts? So that is to say that we think that with our choices, we create a future event, but it's more like rather what we do with our choices is we're selecting from different pasts, and the future then changes accordingly. It's not becoming, it's be-pasting. But anyhow, I want to hear more about your idea of becoming.
Yeah. Good question. What I'm proposing is that if there is a becoming, this becoming is the master asymmetry of time. So the second law of thermodynamics, the cosmological error of time, gravitational, all of them in some way that I still can figure out, they can be derived from it. So becoming is the cause, is the master asymmetry, which lies at the foundation, which underlies all the other asymmetries.
Mm-hmm.
And I want to show you how sometimes you can pick a special past, at least at the quantum mechanical realm. I wish I could, we could pick up another past, but I want to show that at the quantum mechanical realm, you can pick in a very non-trivial way between different pasts and get very interesting results from them.
Okay, let's hear it.
So here it is. Let's take the becoming, just the naive view that indeed time is moving as the very foundation of physics. Forget about relativity, whether how you reconcile it. With quantum mechanics, it will be easier, but let's follow its consequences. And I want to begin with quantum mechanics. And, quantum mechanics it differs from classical mechanics in many, many aspects. It is non-local, it has superposition, it has uncertainty. I would like to propose that one of the main characteristics of quantum mechanics is its extreme time symmetry, such that events can occur and then unoccur. That in quantum mechanics, sometimes you abolish events that already happened in a way that actually they don't exist, that you are changing your past. This is a work by Eliyahu Cohen and myself. And then I think that, and we argued in a paper that this is the key for understanding many oddities of quantum mechanics. For example, the bomb testing experiment of Weidman and myself. So let me show you. Perhaps I'll come back to this later. But here it is.
Okay.
Can you see? I'm showing you two particles which are split by a beam splitter. So on the right, you see an electron. On the left, you see a positron, one yellow, one red. And now this is, I'm following an idea, a very famous experiment proposed by my friend Lucian Hardy many years ago, but with a slight modification. I arranged them such that the left part of the electron's wave function is going to cross the two parts of the positron's wave function. Don't worry about the experimental details, timing, and so on, but it goes like that. That actually they have a chance to meet and then give rise to annihilation at 2 points. Can you see that their interaction is asymmetric? Okay, the electron may meet the positron either at the first intersection or at the second intersection. Suppose that I can make it, and today it is actually even possible to arrange an experiment in which they can meet. Now the question is, because they are in a superposition, you are not sure that they'll meet, right? The electron may go actually to the right and never meet the positron.
Right. And also, if it were to hit this, it would hit the right one or the left one, not both, and it would hit the right one first.
Absolutely.
And the left one later.
Absolutely.
And it will only hit the left one if it did not hit the right one.
Wonderful. Thank you very much.
Okay. Lastly, on the right-hand side, is there a reason that it's going at a slower speed? Or it doesn't actually matter?
No, just out of convenience. Do it just in order to give it a chance, but you can arrange it in another way. So just for for graphical convenience.
Got it.
So you post-select it now. In some cases, you will have an annihilation in the first encounter, and then you discard this experiment. In other cases, you're going to have an annihilation in the other intersection. Okay, you place there two detectors for gamma photons, and you see whether you register them. So you discard these. What about the cases in which both of them do not occur? Now you have an interesting situation. You have made a measurement. So far, they were measuring the position of one another, kind of doing a measurement, whether they're on the right and on the left. But once the two detectors remain silent, you understand that the electron is not in a superposition anymore. It went only to the right. Okay? That means that if you perform an interference experiment with the electron, you will see it sometimes emerging to the left rather than to the right, because the wave function has now changed. Okay? Do you understand it? There is the uncertainty principle says that if you have measured the position, then you have lost the momentum. So in this case, now there is no more superposition. And if you try to combine it, the two parts of the B to this Mach-Zehnder interferometer will be lost. So the momentum of the electron has changed. Do we agree with that?
Yes. Okay. No, wait. Just a moment, please. So all I know is that if you don't see any ticks in the photon counter, that you can deduce that the positron went to the right.
No. Here is the surprise. The yellow is the electron, I think. Yeah. So you deduce.
Oh, sorry.
Electron. Okay.
My bad.
I deduced that the electron went to the right. Now, suppose that after that, I can make an interference experiment. You agree that with the positron, I can make an interference experiment, place two mirrors, and then bring them back, and then I'll get interference. The momentum will be preserved. Okay?
Okay.
A Mach-Zehnder interferometer is a device by which a particle goes through a beam splitter, just like this one. So it goes either to the right or to the left. Then you place two mirrors on the two sides, and then you recombine the two parts of the wave function. So you actually don't know whether it went to the right or to the left. This is the Litzor-Weidman bomb testing experiment. We are basing our work on the Mach-Zehnder interferometer. So this is a Mach-Zehnder. So suppose that I now try to reunite the two halves of the yellow electron in order to get interference. I will not get interference. It will emerge sometimes to the right or sometimes to the left because actually its momentum has changed. Think about the positron, on the other hand. If you reunite back its two parts, it will always go to the right due to interference because it is in a superposition. There is another way that I can show it to you. As you can see, both the right and the left are encountering two mirrors, the electron and the positron. Okay, you can see a mirror. The two solid lines, the black lines, look at the positron on the left. Okay, so the two black lines are mirrors. So if you bring the the two halves of the wave function back, they will always go back to the source. Okay, because you are time reversing the whole thing.
Yes.
Suppose that you do the same thing with the electron, and you place a mirror here and a mirror in the other place where it could have gone has there been no positron.
Mm-hmm.
It will also go back to its. But in this case, you can do the experiment, and in half of the cases, it will not go to the source. It will go to the wall. You have changed the momentum of the electron. This is called, this is not a Mach-Zehnder interferometer, it is a Michelson interferometer. It's a simple one. You split the particle into two and then reflect back the two halves of the ray to the first beam splitter. So of course they'll go back to the source. But as you can see, the electron's momentum has changed. In half of the cases, it will not go back if you reflect it by the mirror. It will not go back to its source, but it will go to the other side, okay? Because one half of the wave function has disappeared.
Right. Now that's provided that you detected no photons, or that's only because of the presence of the two?
No. Suppose that there was no positron and just the electron has been, just as I showed earlier, the electron has been split into two. So suppose I place four mirrors on the two sides.
Mm-hmm.
So you understand that if there was no positron there, the electron would just go back to its source undisturbed.
Correct.
Now that the two annihilations did not occur, you see that the electron is disturbed.
Right.
But now there is something strange. The positron remains oblivious of the whole thing. There has been an interaction here between them. So you had two bodies interacting with one another. As a result of the interaction, one of them, its momentum is changed, and the other remains completely oblivious of this interaction.
Mm-hmm.
Why do I feel that there is a law from 1666 that somehow, that this interaction is not compatible with it?
Right.
Here's Newton's third law of action and reaction. And you see an interaction between two particles. One of them is affected. The other is completely unaffected.
Now, what if someone says, okay, the positron is not affected, but the composite system of the positron tensored with the photon detectors are?
Sure. Still, there is something interesting. You don't have anything like that in classical physics. In classical physics, when you run a process backwards, then either everything is run nicely backwards, or all parties are affected. In this case, actually, you can show that for a while there was an entanglement between the electron and the proton. If one is on the right, the other is on the left. If that one is on the left, the other is on the right. And then actually the path is undone. The entanglement between them is dissolved and the positron goes back to its state. We called it quantum oblivion.
Mm-hmm.
And we showed that many oddities of quantum mechanics, interaction-free measurement, the Aharonov-Bohm effect, the Zeno effect, quantum erasure, and so on, all are based on this capability of quantum events to become and then unbecome. In other words, there has been a time in which there was a virtual gamma photon going to the first detector. It's been there for a while, but then it was undone. The possibility was wiped out. The same with the other detector. So you are correct in saying that there are photons here which we do not see them, kind of virtual photons that could have existed, but they did not exist. All this shows you that in quantum mechanics, there are events that you no more see them, and you don't see them anymore, but they have been there, and the past is in some way being obliterated. I'll give you at the end. I'll give you a reference to some of our works. So this is a work of mine with Liao Cohen from Bar-Ilan University, and it's very detailed, and we give many examples to that. How you are actually affecting the past, and we called it quantum oblivion because it is not we who forget what happened, but it's the universe. Nothing in the positron leaves any mark, retains any mark of the interaction that has been here. So one of the parties is affected and the other is completely out of it. Actually, if you want to understand the bomb testing experiment of Weidmann and myself, this is a paper that has been rejected by, I believe, 4 journals because they said, we've never heard such a nonsense. It is not possible that a bomb that could explode, and just because it could explode, but it did not explode, then it will change the momentum of the photon. And we said, yes, it is, by the formalism. Now, Cohen and myself argue that you can understand the IFM, the bomb testing experiment, and all other kinds of IFM just by that there has been an event, and then it has been obviated, and the bomb or the detector remains oblivious of that. But for a very brief time, there was an event, and then it unoccurred.
Interesting.
This is what I'm going to show in greater detail. So yeah, this is the paper by Cohen and myself, Quantum Oblivion and Master Key for Many Quantum Riddles. And this is the bomb testing experiment. We may say something about it later, but I argue that here is your Mach-Zehnder interferometer. So this is when you asked me, here is a Mach-Zehnder interferometer, okay? Here's a photon going to the beam splitter, going either here or there. And then if there is no bomb here, the photon will always go to the right because it retains its momentum, okay?
Right.
When you make a measurement, then of course you know its position, but then you lose its momentum, and it may go to the other two. So Weidmann and myself said, place not 2 detectors, only one, and make it more dramatic. Place a bomb. In some cases, the bomb will explode, but in other cases, if the bomb is good and the photon went to the left, then you can be sure that the bomb is explodable, is good without destroying it. That was the question that we have asked. Suppose that you have the most sensitive, I guess the Elitzer-Weidmann bomb testing experiment. Okay, you have the most sensitive bomb possible that a single photon can make it explode, but now you're not sure whether it's working or it became rusty and so on. Suppose that you have many bombs like that and you want to make sure that they're okay. So we have showed that, and there is a mystery here. There is an unevent. An event did not occur. Just by the fact that it could have occurred, it leaves a physical trace. The photon goes to the left rather than to the right. You understand why I am not angry at all the journals, the Nature, Science, Physical Review, Letters, and so on, who rejected our paper. I can really understand them. They said, I've never heard such a nonsense. Something did not happen, but just because it could have happened, it leaves a trace. Can't be. And then came Zeilinger and made the experiment, and later got the Nobel Prize. And then Sir Roger Penrose gave us nice publicity, and he also got the Nobel Prize. You better be nice to me. People who are nice to me tend to get Nobel Prizes.
So for people who have just tuned in, they skipped forward to this point, I recommend that you look up the bomb experiment.
Oh, sure.
Many physicists who are quantum physicists, they say that this is more remarkable, more outrageous than the double slit experiment.
Yeah. Okay. And I believe that this is, if you want to have a unified theory of physics, here you have a clue. And I'm going to propose some other clues. This is my mentor. Yakir Aharonov. Is, as I said, is now 92, still active, still very sharp, and he proposed a new interpretation of quantum mechanics, but it's more than an interpretation. We know the existing interpretations of quantum mechanics. Copenhagen, many worlds, guide wave, this one, that one, and all of them give you exactly the same predictions, so they remain interpretations. Their predictions is just like those of quantum theory itself. They just make it more reasonable. Okay. Now came Aharonov and said, I am proposing you a new formalism. It is completely equivalent to the quantum formalism. But lo and behold, when you make the calculations, you are going to get surprising results. Now, these results that you can test in the lab are compatible with quantum theory. However, how is it that no other interpretation of quantum mechanics has derived these results? Do you understand that this formalism is more than an interpretation? It does not contradict quantum theory. But if you use it, you get a plethora of new predictions that only in retrospect people say, yes, this is compatible with quantum theory. But the two-state vector formalism enables you to make surprising predictions that no other formalism would be able to make. And this is why I believe that it brings a very closer to a new revolution in physics. And I want to show an example of that.
Please.
So here it is. Let me go back to the difference between classical physics and quantum physics. This is classical physics. In classical physics, and you mentioned determinism, when I have the initial conditions of a process, I can compute the trajectory and I know exactly where the cannonball is going to fall. Okay? This is determinism. Just make the calculation and you derive the trajectory. So much so that if you shoot it backwards from a similar cannon, you know where you're going to get it, where it's going to land, right?
Right.
It's going to go back to its origin. So here you have two characteristics of classical physics: determinism and time symmetry. They go hand in hand together. The determinism gives you time symmetry. So you don't have to make the calculation backwards. It's redundant. It gives you the same trajectory. Or if you make the real experiment and shoot it backwards at the same velocity, you will get it back at the source. So that's trivial. Okay? So time symmetry and determinism go hand in hand. Things are completely different in quantum mechanics. When you shoot a cannonball, in this case, a particle, you don't know where it's going to land. Okay? So it gives you a kind of a wave, and it may land in several places. And here, if you detect it somewhere and you want to shoot it backwards, you lost time symmetry too. It may go to other places. Okay, so quantum mechanics actually makes you lose both these cherished characteristics of classical physics, determinism and time symmetry. And I've shown that, and now I'm coming to Yakir Aharonov. So this is classical, this is quantum, and now Aharonov proposes the two-state vector formalism of quantum mechanics. Let's call it from now on TSVF. What's new about this? Says Aharonov, make two calculations. Compute it forward, then compute it backwards because it's going to end somewhere. So you have two wave functions. In classical physics, the backward going wave function is redundant. You don't need it. You can use it just to make sure that you did not make a mistake because it doesn't add anything to your knowledge about the trajectory, right? Suppose that I shot a cannonball and you find where it fell, then you compute it backwards. Of course, you will get the same trajectory. So the two calculations give you exactly the same story, okay?
So one way of saying that is unitary, correct?
Fine. Yeah, very good. Thank you.
Now, the two-state formalism, is it not unitary? Or does unitarity emerge?
In a subtle way. Yeah, good question. But unitarity is here being challenged. Unitarity is challenged by quantum mechanics. But in quantum mechanics, people will tell you, just pick the parts of the wave function that did not go into the second and the third cannon, and just bring them together, you may get back you can time reverse the whole thing. But here is the problem, that you can time reverse it. The moment you made a detection, it's irreversible. So I believe that unitarity is not conserved. I won't speak on Aharonov's behalf. You may have a talk with him. I was amazed to hear that Bill Unruh does not believe in unitarity. So, yeah, unitarity is not that sacred. Actually, if we are proposing becoming, then I'll say that every time that you make a quantum measurement, you could not predict it. There is something new coming into the universe, which is just new, which is just being added. We can come back to this question.
Sure.
But now you combine the two equations, and what do you get? The gains. First of all, uncertainty is being kind of outsmarted. Perhaps that at the morning I took a particle and made two measurements, and that one at the morning, one at the evening, and the two measurements are of two non-commuting variables. One, say, position and momentum. Then the TSVF tells you that about noon, for certain, both the position and momentum of the same particle, which the uncertainty principle forbids you to have. Suppose I measured the sigma x spin of a particle and then the sigma y at the evening. They are non-commuting. Okay, so if you measured one of them, the other becomes uncertain, and vice versa. However, at the time between them, now at noon, both the spin of both x and y. Now, have we violated the uncertainty principle? No, because this is now at the past, so it is protected. But it turns out that between measurements, a very interesting physics is happening, which is much richer than the one allowed to you by present-day quantum mechanics. Then I want to show you another thing. Non-locality is now explained. Let me tell you why. Think about the EPR experiment. So two particles go from the same atom. Alice measures this one, Bob measures this one, and when they do something very special, make a choice between two measurements. When they compare the results, it turns out that the choice of Alice has affected the results of Bob, and vice versa. How could that be possible? If you allow the wave function to go backwards, then you have a simple zigzag in the past. Okay, you can see that. So think in 4 dimensions, just as we did with relativity theory. So you have a kind of V going from the past to the present. So you have these two trajectories going in a V shape. So once you make a measurement, you affect not only the future of the particle, but also its past. So it goes back to the origin of the two particles. And then it goes zigzags again to the other particle, kind of. So that gives you this is similar to what Kramer has proposed in his transactional interpretation. So you have a very elegant way of explaining non-locality just by allowing things to zigzag in 4 dimensions rather than in 3. So in 3, it looks local, but in 4 dimensions, in 3 dimensions, it looks non-local.
Right.
But when you think about 4 dimensions, then it's completely local. I think that this is very elegant. Okay.
So in other words, locality is still there. It's just, it looks violated from another perspective.
Right. So that's the second gain. But here's the third and the most amazing. I want to show you a new physics emerging from that with good, interesting results, amazing results. Here it is. So you remember this. I send the particle through a beam splitter, and now I have 2 detectors. So it's a dashed line. I have 2 futures, and I don't know which of them is correct, right? One of them is going to materialize, and the other is not. Okay, it's one particle, so either the right-hand detector is going to click and the other is going to remain silent, or vice versa. And then I wait, and this one clicks. I'm going to call the right side real future and the left side fake future. Is that okay? Now say the Aharonov, run the process, compute the process backwards. If you compute it backwards, so you got a click at the right-hand detector, and now you say, I want to compute the past, of course, you're going to get something ridiculous, right?
Mhm.
In half of the cases, you're going to get it going back to the source. But in the other, just by computation, you get that there was a false origin, say, from the wall or something like that. And if you really do the experiment, say, if you manage to eject the experiment, eject the particle back to the beam splitter, then of course it will not always go to the source. It may go to the other side. So this is a kind of fake past. Okay, we have one fake future and one fake past. So people can tell Aharonov, look, why do we need all this headache? It is enough that we have the fake future here. I don't have to worry about fake past. It's just a joke. I don't have to take it into account. It doesn't add anything to the calculation. Quantum mechanics is hard enough with what we have, with the wave function going forward, rather than having now your second state vector going back from the future to the past. We don't need it. And I want to show, following Aharonov, that you do need it. And here is my claim. Give me a history when you have fake future, as you have seen here in blue, and fake past. But give me an experiment in which there is an overlap between them. What happens when you mix blue with red? What color are you going to get?
Purple?
Right.
Yeah, we both graduated from kindergarten.
And in the purple, you're going to get a real effect, and you're going to be really surprised. So here it is. This is nested MZI due to Lev Weidman, and it's similar to the Mach-Zehnder interferometer that I showed you earlier. Okay, two beam splitters and give kind of this unification, but here it's a bit different. The first beam splitter does not split the beam to half and half, but 1/3 and 2/3. Okay? Then here you have an ordinary Mach-Zehnder interferometer. It splits this part of the wave function into two halves, reunite them. So if you did not disturb it, it will always emerge here. Okay? Perhaps I should have shown a real Mach-Zehnder interferometer. What you see here, ignore the other, is the ordinary Mach-Zehnder interferometer that you see in all laboratories. A wave function going through a beam splitter, going to two mirrors, then being reunited, and then continuing here.
Why is it that it's 2/3 at BS1 on the right-hand side and 1/3?
Okay. So this is a nested interferometer. You have a large interferometer within which you have a small interferometer, which Weidman calls nested interferometer. And the reason why he picked this kind of 1/3 and 2/3, you're going to see in a minute why. Because he's going to use Aharonov's probability. Okay?
Okay.
So these are the possible trajectories of the photon. It's more likely it will go here. In 1/3 of the cases, it will go to this beam splitter and either in this detector or that detector. So you have three detectors, D1, D2, D3, and one of them is going to click. Okay.
The only point that I'm confused about is why is there not a D4? Why is there not another photon detector where F is?
Okay. If you did not make any measurement here, the photon always have to go on only to this side. This is the idea of the Mach-Zehnder interferometer. You send the particle to this this diamond shape array of mirrors. It will always emerge, continuing the trajectory, the momentum that it had when it entered. So if it comes from the left, it will emerge to the right. And as it comes from the right, it will emerge to the left. So you can see here the uncertainty relations between position and momentum. As long as you do not make any measurement to find out whether it went to the right or to the left, so you don't know the position, then momentum is retained. If you try to outsmart...
I see.
Okay? So Weidman proposed a nested interferometer, a big interferometer, small interferometer. This is an ordinary interferometer. This interferometer is somewhat different because the first beam splitter splits the wave function to 1/3 here and 2/3 here. So you end up 1/3 here, 1/3 here, 1/3 here. This is the probability of the particle to be in these places.
Sure.
Now you pick the cases in which detector D did not click. So you have killed all this part of the history, right? You are sure that the photon did not go this way, but this way. And then the other detector does not click. So here is what, So here's what you're going to get. This one did not click, so it went here. You see the solid line?
Mm-hmm.
This is the solid line. That's the only possible trajectory possible, right? Because this one did not click, this one did not click. That's the only thing. So far, everything is fine. Now do what Aharonov tells you and compute it backwards. You're going to get something really ridiculous. This is a fake future. This is a fake future. This is the real future. Now run it backwards and you're going to get fake pasts. Okay? You're going to have the particle either returning to here where it did not come from, or here when it did not come from. Only in 1/3 of the cases, it will go back to where it came from. So you have here fake futures and fake pasts. I really appreciate your patience, because people will say, what on earth is this guy talking about? But now you're going to be rewarded for your patience, because you see that there is a place when the fake future and fake past overlap. Here you have one going forward, one going backwards. The place where they overlap, here, you're going to get a real particle. Not kidding you. I can show you that although no particle went this way and no particle came back from here, there's been a real particle here. We have published a paper in Scientific Reports with 2 Japanese experimentalists who has made the experiment and showed actually with a very delicate kind of measurement by a test particle that, let me show you, there has been no particle here. A test particle found this path empty. This path empty, but here it has encountered a briefly existing particle. How is that possible? I know that, and I urge you, don't believe me. Read the paper. The paper is here. The experiment has been done and verified the prediction of the TSVF. Now, how is that possible? It's possible, and every high school student can understand the algebra. You began with one particle. You ended up with one particle. But for a while, you had 2 particles. How is that possible? It is possible because here you had a negative particle. When you make the algebra, you find for certainty the particle being here when you compute it and being here. But here it gets a minus sign. What do you do with a minus sign? You have to assign it to something. Aharonov chose to do that to the mass of the particle. Now that's very daring. Remember that when Dirac made his calculation and he got a plus sign, he assigned it to the charge of the electron. And people said, look, this is ridiculous. You can't have a positive electron. And he said, if this is what mathematics tells me, I believe it. And he published it. And then 5 years later, Anderson has discovered the positron. Okay. Sometimes you should trust the mathematics. So in this case, it turns out that you got a particle and a negative particle together, which means that actually from the very beginning, one particle went here, one particle went here with its negative twin. Now, it's not an antiparticle, it's a negaparticle because its mass is negative. So you think that you got here nothing. But for a while, you managed to split them. Do you remember how in the case of the Hawking radiation or in the Unruh radiation, you managed to split from space-time, from the vacuum, real particles, one particle and one another, one with positive mass and one with negative mass. This is how the black hole is going to evaporate. It turns out that this happens also in ordinary wave functions, that you have mass more than the mass of the particle. But then you have also negative mass in all these places, such that when you make the measurement, you get only one particle. And in all the other cases, it kind of annihilates itself. Let me stress that I'm talking about a real experiment. I'll give you the sources for your readers to look for them, for the experiment, for the details, for the results. Okay, so trust me here that this is what that this has been shown in the laboratory. Do we understand that there is something new to physics here? Negative mass, something that does not exist in the present particle models, in the standard model. You don't have negative mass. You don't have negative mass for simple reasons, that if you do have negative mass macroscopically, you're going to get all kinds of strange results. Suppose that I have here a rock of negative mass, and then I try to touch it. Then rather than being pushed, it will be pulled. But then Paul Davies have shown that you're going to get velocities faster than light. There are all kinds of paradoxes coming from negative mass. So there are reasons why negative mass does not exist. It turns out, however, that for very brief time, the universe allows negative mass to exist, and that this involvement of negative mass in the evolution and dynamics of the quantum wave function may explain the very mystery of the quantum.
Super interesting. So a question that occurs is that when you have a negative value, there are often different places you can place that negative number. So for instance, with Feynman, you can place the negative on the time or you can place it on the charge. And that's one of the ways that he says you can think of the positron as an electron going backward. Okay. So were there multiple options for what to put the negative on? For instance, could you put the negative on the number operator? So the number operator is usually positive definite. Could you have said it's a negative particle in a Fock space, even though I don't know what a negative value in a Fock space would be?
Good question. It looks like the minus is assigned to the presence, to the very presence of the particle. So it is not that the particle is not there, which is trivial. It is there in a negative way. If you follow it, then you come to the conclusion that if you make a measurement, very delicate measurement, what happens to the mirror that this photon hits, it will turn out that the mirror is not pushed, but rather being pulled. If you make the mirror loose, and this is an experiment that has been done by Lev Weidman, this is called weak measurement. You make the mirror loose and kind of noisy, and you repeat the experiment many times. It turns out that in all the cases that you got your post-selection, you got the mirror pulled rather than pushed. How could it be? Because the particle has impinged on it from the inside. If the particle has negative mass for a very brief time, this is the result that you're going to get. This has also been verified. What I'm arguing is that the TSVF has produced now a plethora of so many surprising results that actually a new physics is going to emerge from them. And what Eliyahu Cohen and myself are proposing, and we are now closing a circle. Lev does not agree with me. Lev Weidman, whom I cherish and love very much, he said, no, I believe in the many worlds. But what we have said, if you want to understand how a bomb or a detector changes the course of a particle that never hit it, okay? You have this photon going in the Mach-Zehnder interferometer, the bomb is only here, so it's obvious that the photon took only that side, so how could there be an interaction between the photon and the bomb? What actually this story tells you is that the photon went 3 times through the Mach-Zehnder interferometer. It went on the right, it went on the left, but it also went negatively on the left. So for a brief time, there was interaction between the photon and the bomb, but it was undone. We have a very detailed analysis of that. And there is no physics here, because here Weidman shows you how for a very brief time between this particle and negaparticle, where you think that there is nothing, just like, in the Hawking radiation or in the Unruh radiation, you manage to split for a while what you think to be a complete nothingness to get a real particle out of nothingness. This is what happens here. We called it non-local position changes of the photon revealed by quantum routers. And actually, there is now a more advanced experiment by Ryo Okamoto and Eliyahu Cohen. If you give your readers, your viewers, references, I'll send you some references such that they consult them. I beg all your viewers and you, don't believe anything I say. Read the papers.
Right.
There are theoretical papers, there are experimental papers, read them.
So the links to all of what's been mentioned in this podcast will be in the description. So 2 questions occur to me.
Yeah, go ahead.
You said that this reproduces quantum mechanics. So what would be the standard account? What would be the standard reason that this occurs?
Very good question. Very good question. I asked Lev, how can you explain that? So he gave an explanation in terms of the many worlds. There is a universe in which for a while there is a particle, but this is no more our universe. You better ask him. I would love to see, and I challenged both John Kramer and there is another Ruth Kastner, and I said I would love to see an analysis according to the transactional interpretation of this result. I would love to see, by all other Copenhagen, all interpretations like von Neumann involving human consciousness, whatever. I'd love to see their analysis of that. I find that actually the two-state vector formalism is a formalism that does not invoke any the guide wave or entities that you can never prove. It tells you that if you allow in 4 dimensions things to go back and forth such that mass can sometimes become negative, then you get a very interesting, very intuitive explanation, plus, and that's the most important thing, plus new results. So you ask a very good question, because in retrospect, quantum formalism must confirm that. Now I'm going to ask, how come that none of the other theorists, from many worlds, from hidden variables, Bohmian mechanics, and so on, how come that none of these interpretations have come with this prediction? It tells you that ontologically, the TSVF is closer to the truth in some very deep ontological sense. Let me say the following. Once we have a new theory, which will come instead of quantum mechanics, once we have the long sought for revolution of quantum mechanics and relativity, that will be an ingredient of that future theory that we don't know yet about. The things go on both sides, on both directions, a long time.
This is super interesting. Now, is this yet at a rigorous stage?
So there are speculative parts of this talk, and there are rigorous parts of this talk. This is rigorous. This has been published in Nature Scientific Reports, and then there is a consecutive paper which is experimental, beautiful results, and they just show what we claim, that you have a path where no particle went to and no particle came back for, but for a very brief time it has existed there. And that comes out of understanding that in that wave function, which has been split into 3, there has been a negative part in which mass itself was negative. That, with all modesty, I would beg people of the standard model, why don't you think about this possibility that mass sometimes can be negative? If this is brought to your symmetry groups and so on, that may give you new hints for the theory that you're looking for.
Okay, that's in many ways an explosive presentation so far. So explosive not only because of the analogies that we've made. So mine was dynamite, and then you had a bomb and then a cannonball, but also in terms of results. So let's see where else this goes. Take me on the rest of this journey.
Very good. So now I'm leaving quantum mechanics. When we want a theory, a unified theory, we want to think about relativity. So I'm going back to the basics of relativity, quantum mechanics. Let's put it aside, and I'm going to ask a question about relativity. You remember that in special relativity, the velocity of light is invariant, which, for a freshman, fresh person in physics, this is really surprising. I am measuring the speed of light and I get the speed, which is c. Then I travel very fast towards the source, such that now I should get a much higher velocity, and it's just the same. Then I run away from it, almost at the speed of light. So it must be much slower, and I still get the velocity of light. So there is something very counterintuitive here. Galileo has shown to us that all motions are relative. Einstein agrees with him with the one exception. The velocity of light doesn't matter whether you travel fast or slow to one direction, to the other direction, contrary to the direction of the light, the same direction, you will always get the same figure, 300,000 kilometers per second. And that's really strange. Now, the question I'm going to ask is a kind of, high school student pupils question. What makes light so unique, so special, that this is the only velocity which is completely invariant? Here is what not. Some people will say, we see only with light. But I mean, relativity theory is not a theory about human beings, about their eyes, about their senses. In other words, has there been an Einstein bet? And he would try to base his physics on the assumption that the velocity of sound is invariant. He would utterly fail. Do we agree with that?
Right.
So, what makes light so special? Einstein, the young Einstein was a positivist, and he may give you the answer that we see it through light. But the old Einstein, who was not a positivist, and he was looking for a deeper understanding, he never said that. But I take the liberty of talking on his behalf. The same velocity invariance holds also for gravity waves. Okay, we have gravity waves. They travel at the same velocity. Nobody thought about doing this experiment because it's very hard to measure gravity waves. But suppose somebody measures the velocity of gravity wave by moving very fast, close to the velocity of light, towards the source of the gravitational wave. He will get the same number, 300,000 kilometers per second. Do you agree with me?
Correct.
And vice versa if he runs away from it. So this invariance holds not only for the velocity of light, but also for the velocity of gravity waves, not only for electromagnetic waves, but also for gravity waves. That makes relativity much easier to understand. What is invariant is for the causal connections. Photons bring about causal connections. When you use a ruler, when you use a clock, the reason why the ruler has this length is because photons run between the atoms, back and forth from the quantum mechanical perspective. Okay? When I sit on the chair or when I hit the table, I don't get into the chair, or I don't get into the table. There is a mechanical interaction because they exchange photons between them. Do we agree about that?
Right.
So photons are the carriers of interactions between the objects here. Gravity waves, are the carriers of interactions between galaxies and planets. So what is common to the two waves, the electromagnetic and the gravitational, is that they are the agents for causal relations. It is photons which maintain the length of the ruler. It is photons that actually keep the clock, the mechanism moving, being exchanged by them. So that's the reason why this velocity of light is so unique. It is the interaction. It is the velocity of interactions between bodies. I know very little about the strong force or the weak force because they hold only for very strong distances. So we can leave them aside. But that is important for what I'm going to say later. And once again, I propose the assumption of becoming. I say, let's combine relativity theory, although it does not follow forcibly. It's just an assumption that events are created anew, one after another in space-time according to their causal order. At any moment, time, there is a time which is perceived as now. Future events are not only unknown, but objectively inexistent. And they will be created. Coming back to your dishwasher, whatever you and your wife are going to do with it, this is something that is going to emerge. It's not already there. I'm sure that your wife would agree with me. You can.
So this moment of now,
Yes.
Is this a moment that is shared across people? Is it local? Is it within some open patch? Or is it just at a point there's a now?
Good
that is,
question.
for every observer, they have a different now.
Good question. Hermann Weyl, he grappled with this problem and he proposed that the world is block universe and we are world lines from birth to death. But there is something called consciousness and it crawls up the world line. He was a genius mathematician, so he believed in in relativity theory and in the block universe, but he said perhaps there is something which is outside of physics, something, as you said, about this fire going through the dynamite rope. Okay, so Weil believed that there is something called consciousness going up there, crawling upwards. Why? Nobody understands. Now, Penrose once joked and said, when I'm talking to you, is it possible that my now is already ahead and you're just talking to a zombie? Or your consciousness is, is the crawling of our consciousness simultaneous, or is it relative? Good question. I'm going to say something about it. But I suppose that there is indeed some kind of now moving forward. Objectively, what kind of physics is going to emerge from it? I'm going to use Mach's principle. You know Mach?
Yes.
He gave Einstein the impetus to produce special and especially general relativity. And he said there is no meaning to time or to space if there are no events. You can't talk about empty space just being absolute. There are events in it, and the distance or time intervals between events, this defines distances, space distances, or time intervals. Now I derive from this principle the following claim. If I believe that future events objectively do not exist, whatever you do with your dishwasher, whatever I'm going to do tomorrow with my cat and my car and whatever, or my daughter, whatever, these events are not there. That means that space and time do not exist beyond the now. Now, I think that this is interesting. If there are no events, then there is a limit to space and time. They don't exist beyond the now. Now, why do I feel that there is a cosmological ring to this? I mean, the whole universe, the 4 dimensions have emerged. They are expanding. So when I say that the now is moving forward, actually, I'm saying that there is an expansion of the universe, not only in 3 dimensions, but this is also the expansion in time. There is more and more time, just as there is more and more space to the universe as it expands or even inflates.
Mm-hmm.
There is more and more time to the universe as the now moving forward. So actually, it is space-time which is being created by the now. There is more and more space-time out of nothingness. When a student asks you, what is outside of the universe? You say it's meaningless. It's an interesting question, but it's meaningless in terms of present-day physics because this is space-time. When you say out of, you're already assuming space. So it's meaningless. It's the universe. That's the whole story. Nothing beyond that. Once again, so the future is the nowhere, is the no-when. There is nothing there, not even space-time. And actually, as the universe is expanding, just I'm following the Big Bang, it is also expanding in time. So I think that I can avoid the threat of infinite times if I show that I'm not assuming a higher time parameter when I talk about this creation. Look, it's similar. People ask you what happened before the Big Bang. So it's not a silly question. It's a very profound question. We just say time was created at the Big Bang. So at present, we can answer that. But we do understand that space and time are being created.
Mm-hmm.
And when you understand that the assumption of becoming is very natural within that. Actually, the Big Bang is occurring even now. I mean, at any moment, there is a new layer to the universe. It is, as it expands, it also grows in time. That may have interesting consequences.
So let me just see if I can recapitulate this point. So if you look at a Penrose diagram, which I'll show on screen, what people see when they think about the Big Bang is at the bottom, and then there are some photons that come out, and then it's at this squiggly point that you wonder, okay, well, what happened before? And then physicists like to say there was no before. You're making reference to a time, and you're making reference to a space, and so on. And then eventually physicists start to accept that, and maybe even the people who ask the physicists start to accept that. What you're saying is that physicists also like to think of the future as infinitely extending into the future, but you could also think of what is now as equivalent or analogous to how the Big Bang gives rise to moments. Is that correct or no?
No. You told me what I think. I didn't know that I think that this is what I think, but it turns out that this is what I think. Thank you for telling me. Yeah, that's another way to put it. I never thought about it. So let me think about it. Thank you. Yeah, I think that that's a very good way to put it. Now, of course, we have here a philosophical problem or a logical problem because Kant told us that time and space are necessary forms of any thought, and also for any PowerPoint slide. Okay, when I am trying to show this nothingness, how can I show it? I still need to put on my slide some kind of space, although it's not there.
That's actually extremely clever. I like that. Does that get laughs at conferences?
If they are good physicists, they laugh. Sometimes they give you a funny look and say, "For God's sake, when is this talk going to finish?" But but you know, Kurt, much of the material that I'm showing here is thanks to you, is new. During the 2 weeks, we tried to have this talk, and then there was a technical problem, and you said, "Let's reconvene." What do you know? Because of that, I said, next time I better prepare my talk, and then my thoughts began running. So much of what I'm showing here. So I'm thankful to you. And next time I go to a conference or I write a paper, I'll have to give credit to this podcast.
Wonderful. So I just had a podcast with someone named Manolis Kellis, and he was saying that often mistakes.
Oh, the biologist. The biologist.
Right.
Oh, he's that guy is amazing. Yeah, I'd love to talk. I have some thoughts about biology too. If you're interested one day of talking about life.
Well, I can arrange a talk between you and him at the same time on the channel.
Wow, that would be great. That would be.
Okay. And so anyhow, he said mistakes in conversations can precipitate new ideas. How? Because I gave the analogy, but he was suggesting this. But the analogy is that if you're having a conversation where everyone's interpreting each other correctly, it's as if you're playing badminton with one another or tennis, and that's great. But if the other person misinterprets the other person, it's as if you didn't knock the ball back to them, you knocked it off to the side, and now you have to go and find the ball, and now you've explored a new part of the town or the city that you wouldn't have gotten to had you done everything correctly initially. So with us, had there been no Riverside issues or Zoom issues or online technical issues or microphone issues or what have you, these ideas may not exist. So that's pretty cool.
Yeah, you can direct Professor Manolis to Murray Gell-Mann's book, The Jaguar and the Quark. He says an interesting thing that once while giving a talk, he made a slip. And he said another word rather than that one. People giggled and they corrected him. Later, it turned out that he had a new idea. So it was there in his unconscious and went through one of the slips of tongue. And Professor Manolis knows he will say that this is how evolution progresses. There are mutations, most of which are lethal, but very few of them turn out to be ingenious for what comes next. So yeah, this is what happened to me.
All right, let's get to the rest of the slides.
Yeah. So here is the naive view of the block universe. I'm showing here, say, an annihilation between a particle and antiparticle. So it's the blue, purple, whatever, and the red, and then they give rise to a photon, and the photon hits another electron, and it scatters off. Okay, that's the naive view. Past, present, and future, they're all together. Now, if I want to make a becoming of that, I should say that there is nothingness. The universe does not exist. This is the black thing. And it slowly or quickly unfolds, and then we get such that the world lines are being drawn as the universe expands. That's kind of naive becoming. Now, go to your question. Is it universal? So first of all, now I'm going to come full circle with quantum mechanics. And you say always, look, this quantum mechanics is really strange. I have a wave function going in all places, and I know that it's real. In many experiments, like the bomb testing experiment and so on, you know that the particle can be in many places like a wave, but then when you make a detection, it's only in one place. It's only in one place, but it did not go all the way to that place. There was a collapse of the wave function. It resided in many places, and the moment it was measured, it was there. That is really strange. What I'm proposing is that it is strange because you think that there is a pre-existing space and time into which this wave function goes and then gives rise to this collapse and to many places which are empty. Okay. The photon is not here, or the particle is not here, not here. So you have an empty space. It is only in one of the possible spaces. All the rest give you empty space. And here is my suggestion. Is it possible that the empty space is also created by the space-time? I know it sounds crazy and you may regret for calling me to your podcast. But I'm proposing, once again, the following. You send the particle to what you think is a vacuum. Okay, there is nothing there. And then you have a wave function going to the vacuum, and then you make measurements and you find it only in one place. All the other places are empty. So there is nothing there. There is space and time. Is it possible that the wave function actually creates not only the particle, but also the space-time surrounding it? So collapse gives rise not only to the particle in the location, but in all the points in empty space where it could have been. And then, so here it is. Here you have particles. They interact with one another. Sorry for this silly thing.
No, that's cool.
In that nothingness. And then you have particles and the space-time around them. And once again, they interact in the nothingness, and then you have space-time around them. So what I'm proposing is that the quantum interaction precedes space-time. Space-time emerges from the interaction, whether these are photons or gravitons, or perhaps even the real particles. I'm not completely sure about that. I say that electromagnetic waves and gravity waves shape our universe. They shape our rulers. They shape our clocks by exchanging photons between them, because this is electromagnetic. And when you are talking about the universe, there are gravitational forces between them. Is it possible that what creates the empty space is just these gravitons and photons, their wave functions that actually interact with one another in the nothingness? You know, when I talk about nothingness, you see this black part.
Mm-hmm.
It is similar to the nothingness outside of the universe. You can't go out of the universe because the universe is space-time. We are bounded by this nothingness.
Right.
And I guess that this is how I would propose that space-time is emergent. And so on. Now, so this is the speed of causal connections. I'm not surprised that the velocity of light is always the same, no matter how I travel, because when I travel, my world line and all the force-carrying particles, whether photons or gravitons, interact with the environment. So they create the space-time between them. Now I am not surprised that when I measure the velocity of this force-carrying particles, it is invariant. And now I think that we are going to get the great reward. So mass gives rise not only to space-time curvature, but also to the bumps in the plane. So you ask whether this now is always the same. Frankly, I don't know. I would guess that every time that there is a mass, then somehow this simultaneity will change and time is moving differently in that place. This is not Schrödinger's cat, but
Right.
And now something interesting. Think about the EPR experiment or Schrödinger's cat. I think that now you have a good explanation to them when you say, and this goes to your question about whether time is simultaneous or not. When the time moves, you see that it leaves some corridors which are not filled yet.
Okay.
And these are the two corridors of the two particles. As long as you did not measure them, there is no space-time there. The moment you measure them, then evolution, the now goes and fills the gap that you have left in this corridor. I look at the Schrödinger cat, and a student many years ago asked me a question, and she was it was a very bright question. She said, "Why are you physicists so much bothered about Schrödinger's cat? You want to know whether it was superposed or not when the box was closed. I can show you that he was not in a superposition, because all you have to do is to make the experiment longer, say 3 days, and then open the box after 3 days. So the little event which occurs or does not occur has to occur at the beginning, and then you wait for 3 days and
Right.
open the box. Then you're not going to find only a live cat or a dead cat. You're going to find a live cat, but very lean, just like this cat, very lean and angry and all droppings and so on. Or you are going to find a dead cat, but already decomposed.
Right.
So she said, "Why are you bothered about that? Do you agree that this is a very profound question?" And my answer is that as long, you see this rectangle on the left, as long as the box was sealed from the rest of the universe, there was no space-time there. The cat being superposed means that its evolution has stopped. Now, when you open the box, becoming goes back and fills it. So actually, you're creating back the whole history of the cat. When you're opening the box, you are not only determining the cat's state, but you are determining its entire history. This is very similar to John Wheeler's delay choice experiment, in which you have a photon coming from far millions of years ago, and then now by making an interference experiment or just measuring its position, you are actually choosing the kind of history that you have. But I'll be happy to talk about Wheeler's delay choice experiment another time. But actually, the idea of becoming actually tells you that many of the quantum mechanical problems can be better understood in this way. And here, before I finish, I come to the most, and then the origins of time asymmetry, all the asymmetries. There are important books by Davis and others, the physics of time asymmetry, what is the master asymmetry. So I would say that it is becoming. But now, how about, and with this I come to the conclusion, if two particles, what I propose here is that two particles interact with one another in the nothingness outside of the universe in a way that I don't know how to describe. It's beyond, you need very strong mathematical tools, and cosmologists may have it when they talk about the origin of the universe, kind of pre-state in which the universe exists, or how universes are born from one another. I'll talk about it later. But if you say that the quantum mechanical interaction occurs beyond the now, in the next moment, where there is nothing, there is no time, no space, and then space and time emerge by this interaction, you're going to get their relative positions, which means that you're going to get attraction, repulsion. They come very easily for this. They don't have a position yet. They don't have a momentum yet. It's only they interact in a very mysterious way outside of space-time. And then there is a collapse, and then the whole space-time is there. Do you understand that you can get gravitational attraction or electromagnetic attraction and also repulsion coming naturally and smoothly from these dynamics?
It's not entirely clear to me.
You have world lines. And according to relativity theory, the naive relativity theory, the world lines are just there. Past, present, future. Now we are proposing that there is a now which draws the world lines. Okay. And I suggested that they interact with one another quantum mechanically. You see, the black realm is where this is the now. And I suggest, and out of it is just like out of the universe. I mean, the future is just like out of the universe.
Yes.
No events, but there is no space-time. Space-time is being created, is growing. Now, when I suggest that the wave function creates not only the particle, but the space surrounding it. Remember that in general relativity, actually, there is an interplay between mass and the space-time surrounding it. Here, I'm proposing similar thing in quantum mechanics. There is a particle, and it gives you a wave function. And as long as you did not make a measurement, it may be in many places. Then you find where the particle is, and all the other places are empty. I suggest that the collapse of the wave function, or whatever it is, gives rise not only to the particle, but to all the space where it could have been there. So the empty space is also a product of the wave function. Now, if a particle creates the space and time around it, do you understand that attraction and repulsion now, the relative positions of particles or bodies, planets, can be better understood in this way, that space-time is being curved, but the curvature of space-time is due to interactions which are outside of space-time. They are first quantum mechanical, and then when there is kind of measurement or collapse, and then there is becoming, then you have the body, whether it's a charge or mass, and it has a new relative position to the other body, to the other charge or mass, because they have created the space-time around them.
Okay, I see what you're saying. So are you saying that the filling in of space, either if it's filling it in between two particles, that's repulsion, if it's filling it in outside of the two particles, it's pushing them together?
Yes.
Okay. The trouble with that would be that if you were to see two particles being repelled, shouldn't you see every other particle that was between them also being repelled?
Why should I?
Because space would be growing between them, or you could also see them attracting?
No, yeah, good question. I mean, in vacuum, there is no problem. I would argue there have been
Right.
photons exchanged between them and they created. Now you may ask me if I do it in the laboratory. Good question, Kurt. Thank you. That may show that my whole model is wrong, but let me think about it. I'm doing it here in my room. So I have a electron here, and they repel one another. But there has been air here too. And there are tables and this cat, and so it's not in vacuum. No. Actually, I will have to think about all those particles of air and the furniture and this guy. They're also evolving. So they are also evolving together, and they are also interacting. So that's very complicated. I agree. That actually can give you, we don't have the resolution for the measurement problem. Okay. Can a particle be in a superposition? Yes. I made money of it. This is the Elitzur-Weidman bomb testing experiment. Can a cat be superposed? No, I don't know how to do that. But people say that if you manage to put this guy in a box where it is completely isolated from the universe, you can do it on Earth, but say in outer space. And of course, you don't want to make an experiment that will kill it, but just tickle it. How can you get a cat being superposed? I mean, it's macroscopic. You have to go to outer space, and then it will be superposed. To your question about repulsion of two charges here in the room where it is filled with air, my answer, and thank you for asking me, is that all other molecules, all other particles take part in this story. They all send either photons or gravitons, actually both. Everything sends gravitons, even if you're a single electron. So they are sending gravitons, photons, and other force-carrying particles. Let's not go into the nucleus. And then it is these interactions between them by these force-carrying particles, bosons, which create the space around them. So if you do it here in the room, it's going to be very dense, very crowded. But the same thing happened. You just have many, many more partners to this.
I need to think about this some more. This is extremely interesting.
Me too. So let me just end and say, yeah, and then we can have a free talk. What I'm suggesting is that, and it's a kind of research project. I say to to cosmologists, and this is something that I could not understand. So the wave function upon measurement gives rise not only to the particle's position and momentum, but to the entire space-time region in which it could have resided. So the pre-space-time interaction determines the distance between objects. This is how you get attraction and repulsion. The research program would be to ask cosmologists, and this is something in which I'm fairly ignorant, about their scenarios of pre-Big Bang, what happened before the Big Bang, because for many years this has been considered to be a non-question that you can't ask.
Yes.
But nowadays, cosmologists do ask it. They talk about how the universe emerging from one another, evolving from one another. So there must be some more fundamental reality within which Big Bang and universes are born and perhaps die and so on. I think all I'm proposing here, and once again, I'm thankful to you to make me realize that this is what I'm proposing. Whatever you think happened before the Big Bang, it's just happening in the next moment, which is not existed. So we are always facing this kind of out of space-time that was before the Big Bang. And then there are interactions, quantum mechanical and so on, between force-carrying particles, and there is a new layer of now. And it's very surely it's not straight, but gravity and other things, or the corridors that I've shown, at a very low scale, still keep such that the becoming sometimes go back and forth to these zigzags. But very likely, when you want to understand what gravity is doing there, we know that clocks tick more slowly in gravitational in where gravity is high. Very likely, you have this line of now being somewhat having these bumps according to the presence of mass, and very likely also to charges in a way that we don't understand. What I'm proposing is we would love to see, so here it is. General relativity did something wonderful. It showed that gravitational attraction is just, the bodies are following Newton's rule. They are going in straight line. It is only the mass, it is only space-time which is being curved around the mass. So you have this beautiful interplay between space-time and mass. Space-time tells mass where to go. Mass tells space-time how to curve. We would love to have the same account with colonic forces, attraction, repulsion, magnetic, electric, and we don't have them. Einstein was sure that he's going to have them within very few years, and so far he failed. I know that it's very bold, very ambitious, and even arrogant and impudent of me to suggest, but it's about time to do that. Think about becoming, with all due respect to models of many, many spatial dimensions which are compactified and so on. Take becoming as your starting point, and then think about this one as giving rise to attractions and repulsions. And I believe I gave you reasons to think that actually these are the carrying forces, electromagnetic and gravitational, which they perhaps precede space-time. They are more basic than space-time, and space-time is created by them. That offers a new way to look for a unified theory.
Professor, that was wonderful.
Thank you. I wanted to say something about compactification. Some cosmologists say, string theory say that, many of the dimensions are compactified, and they became compactified after the Big Bang. Perhaps every such creation of space-time leads to this compactification and wave function collapse. And let me finish with this. You asked me about Minkowski and the controversy that he had with Einstein. I don't think that there was a controversy. It's interesting to know what were the personal relations between them. Perhaps we may find one day a no letter or no email, but something like that.
Mm-hmm.
But you know that Minkowski died very young, from diabetes, from appendicitis, which is terrible.
Hmm.
How did humanity lose such a huge genius of this simple condition? And you know what he said? He knew that he was going to die. And it is quoted as saying, "What a pity to die at the dawn of relativity." So, the dawn of relativity is over now. Relativity is up there in the sky, but there is a new dawn always. And let me wish you and your dear wife and everybody that it will be always a pity to die and that there will always be a new dawn waiting for us.
Well, Professor, I have a variety of questions for you, some technical, some about what advice you have for students. So, how about we save the technical questions for next time? And if you're watching and you want to ask the professor some questions, you leave them in the comments because there'll certainly be a part 2. There may even be a part 3 with Manolis himself, maybe you with another physicist. We'll see. But either way, please end this with your advice to the young physicists and the young mathematicians, people who are entering the field, and then also people who are currently researchers, as that comprises the bulk of the Theories of Everything audience.
Yeah, some of my advices, some people will tell you that they are not good advices, but yeah, this is what I did. First of all, don't worry about your salary. People will tell you, why do you do that? You better go to study AI, solid state, quantum computation and so on, because in high tech, you're going to get much better salaries. If you go to study foundations of physics, you have to be very good. And there are few positions. And still, my advice is don't worry about it. If you really love physics, if you really love theoretical physics, if you love the foundational questions, be ready to put up with a somewhat lower salary, with a somewhat slower progress in your career, but the gains are there and it's worth gambling. If you're good, don't worry. Even if you have an idea, if you have an hypothesis and it is not proved, don't worry. If you're good, if you're smart, if you love physics, if you love science, you will find interesting things. Columbus never knew that he is discovering America. He thought that he found India, but he was just looking. And when you are adventurous, you will find things. So don't worry about that. Don't be afraid of asking simple questions. We have a problem with the tenure track in all universities. You finished your PhD and then your postdoc, and then they give you 4 or 5 years. You have to produce a certain number of papers that people measure them by the impact factor and so on in order to give you tenure or not. Very often, people do not dare to ask fundamental questions during this time because they have to produce papers. I wish I knew what to propose to you. You should have survived. You should survive in the system, publish, but never lose touch of those profound questions. And another thing, make groups, study groups, young people, boys and girls, young students. If you love a certain science, history shows that whenever you make a group of people saying, let's meet every Wednesday, let's go to a certain cafe, you read this paper, I'll bring this book, let's read them together, let's think. If you have a theory, we shall be your peers and so on. Nowadays, it is easier to do it with Zoom. It's very good to have dialogue, especially with people with your age. Young people together can be, without fearing the authority of the professor, and every once in a while going to consult a senior scientist, but do fertilize one another. I find this extremely important for the development of scientists.
I agree about studying and thinking in a group. So for myself, that's something that I wish I had done when I was an undergrad. Even now, I'm a lone wolf, and virtually every single thing I've learned in physics and math and philosophy, I've learned on my own. I didn't even go to lectures. I just would study on my own. And it's painful and slow. And recently, there's some problem that was bugging me for months. And then I went to film with Manolis, as we've mentioned in this podcast at MIT. There was a student there. I told him my question, and then he just started answering it. Then I was like, okay, I understand now. And that just took a few minutes. Whereas if it was just me, I would be toiling over the course of days, not in a row, but intermittently over the course of days and weeks. I mean, I had this problem in the back of my mind for months, like I said. But anyhow, that's something that I wish I had done.
Friendships are very important in science, and the good relations of friendship and love between people who are going together, it's always a very good fuel for the intellect, that you do it in such an atmosphere. Very stimulating. And nowadays with Zoom, it should be even easier.
Professor, I'm grateful that we've established this friendship, and I hope to continue it. I look forward to speaking with you again.
Thank you very much, Kurt. Looking forward to it. Great meeting you. So talk to you soon. And once again, thank you, because there's going to be a paper soon. I'll have to think about it, and I'll deliver it. First in a conference, I'll look for an opportunity, and then a paper. So in all of them, I'll make sure of just pointing out that it wouldn't come out. And this is what I say to our viewers: make friendships, make contacts, interactions, because this is how Einstein, actually, one of his ideas for the general theory of relativity was that he wrote an encyclopedia entry, and then he had an idea. So we were lucky to have this.
Take care, sir.
Okay. And it's about time you call me Avshalom, Kurt.
Avshalom. Thank you.
Namaste.
New update. Started a Substack. Writings on there are currently about language and ill-defined concepts, as well as some other mathematical details. Much more being written there. This is content that isn't anywhere else. It's not on Theories of Everything. It's not on Patreon. Also, full transcripts will be placed there at some point in the future. Several people ask me, hey Kurt, you've spoken to so many people in the fields of theoretical physics, philosophy, and consciousness. What are your thoughts? While I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. Also, thank you to our partner, The Economist. Firstly, thank you for watching. Thank you for listening. If you haven't subscribed or clicked that like button, now is the time to do so. Why? Because each subscribe, each like helps YouTube push this content to more people like yourself. Plus, it helps out Kurt directly, aka me. I also found out last year that external links count plenty toward the algorithm, which means that whenever you share on Twitter, say on Facebook, or even on Reddit, etc., it shows YouTube, hey, people are talking about this content outside of YouTube, which in turn greatly aids the distribution on YouTube. Thirdly, there's a remarkably active Discord and subreddit for Theories of Everything, where people explicate TOEs, they disagree respectfully about theories, and build as a community our own TOE. Links to both are in the description. Fourthly, you should know this podcast is on iTunes, it's on Spotify, it's on all of the audio platforms. All you have to do is type in Theories of Everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comments that, hey, TOE listeners also gain from replaying. So how about instead you re-listen on those platforms like iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. And finally, if you'd like to support more conversations like this, more content like this, then do consider visiting patreon.com/KurtJaimungal and donating with whatever you like. There's also PayPal, there's also crypto, there's also just joining on YouTube. Again, keep in mind, it's support from the sponsors and you that allow me to work on TOE full time. You also get early access to ad-free episodes, whether it's audio or video. It's audio in the case of Patreon, video in the case of YouTube. For instance, this episode that you're listening to right now was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough. Thank you so much.